My name is Victoria Contreras, and I am in Greco's Lab M class for Physics 2111. I went to the Baseball and Physics lecture by Alan Nathan. This lecture was extremely interesting to me just because it allowed me to see how much physics is integrated, obviously, into our everyday lives. It's interesting to see how we can analyze mundane tasks like baseball, something that I've grown up with. And just be able to make predictions or see what occurs. So let me start off with the bat-ball collision. This is something he started off talking about, and you can see he talked about a lot of physics concepts here. So for example, we talked about impulse, how there's when you hit a bat in a baseball, it's a very short amount of time, less than a millisecond, but a very large force, and that gives you a very large impulse. And you also talked about the energy changes. When you have a baseball coming towards the bat, it obviously has kinetic energy. When the bat and the ball collide, the ball compresses. So you have the potential energy, almost like a spring. And then when it comes back out, you have the kinetic energy again. Going from that, you have the conservation of momentum. In the lecture, he gave a diagram of the bat and the ball being analyzed, and you could watch as the ball came, and once it hit, the bat slowed down and the ball sped up. So you could see the conservation of momentum there. And then finally, dissipation of energies. He talked about how inefficient actually the system of hitting a bat and a ball is, just because you lose energy through the vibration of the bat or through the distortion of the bat and the ball. So he talked about how much of an inefficient system it is. So during the lecture, he gave us an equation for a bat and ball speed. And obviously you can see the equation here. It's q times the velocity of the pitch plus 1 plus q times the velocity of the bat. So it depends on the bat speed, the pitch speed, and the collision efficiency, which makes sense. He actually mentioned how the velocity of the bat actually is a lot more important than the velocity of the pitch. But he gave some numbers. Say if you have a pitch of 80 miles per hour and then when it is hit, or the 75 miles per hour, afterwards. He said that, okay, yeah, this goes back to, these are regular numbers, so you have like q equals 0.2, and 1 plus q equals 1.2. This is about usual, which is interesting to see because, say, if you had a perfect efficiency, a perfect ball, perfect bat, you'd have 1. But you see it's only 20% of that, so just pointing out, again, how inefficient of a system it is. But what is the collision efficiency? So the collision efficiency depends on 3 different things. It depends on the weight of the bat, so mostly the moment of inertia, how easy it is to swing it, and all that good stuff. Also, however, depends on the coefficient of restitution, which is just a fancy way of saying how bouncy the ball is. So he showed a quote-unquote super ball that he dropped it and it just about reached back to the initial height when it hit the ground, so it bounced back up. When you do that to baseballs, the baseball only bounced back up to 1/4 of its height. So baseballs have about 0.5 of a coefficient restitution. This means that they lose about 3/4 of the energy, and this is obviously not a very efficient system again. But so the higher the coefficient restitution, the better it is to hit the ball, basically. And then lastly, the bat matters. If you hit the ball on the sweet spot, or the spot on the bat that has the least amount of vibrations, the lowest amount of vibrations, then you're losing the least amount of energy. If you don't lose a lot of energy, then you're gonna be able to hit the ball farther. So if you've ever played baseball, you know that whenever you hit the ball wrong, you can feel the bat vibrating in your hand. It hurts, it sucks. So it's just a matter of when you're doing that, you lose energy and you don't play as well. So that was pretty interesting. Okay, so one of the questions was, which is better, a wood or an aluminum bat? Survey says that aluminum bats are the best. Surprisingly though, it's not because that they're hollow, because they are hollow, which gives them a higher bat speed. They're easier to swing, but the collision efficiency is lower. The reason they are better is because they have a sort of trampoline effect. Wood bats, they have the rough surface, so when the ball and the bat collide, the ball compresses more than the bat actually does. When you use aluminum bat, the aluminum bat compresses, and then that compression is easier to give back energy to the ball. So as you can see, I have a little chart over here that just basically shows the difference in the distances. So obviously aluminum bats are better if you want to go out and play some baseball. One of the last things he talks about was forces on a baseball. So the different forces on a baseball are the Magnus force, the drag, gravity, and air resistance. So I've never heard of the Magnus force before. It's perpendicular to the velocity. As you can see, it is he said it was it's the force that allows a rotating ball to rotate. And then obviously you have the drag. It's going to be opposite of your velocity, slowing the ball down. You have your gravity, which is bringing the ball towards the earth, and then your air resistance. He mentioned how the air resistance is actually more important than the Magnus force, and how that's very interesting just because, in Physics 1, we neglect air resistance majority of the time. So it's interesting to see how important it actually is and how wrong our approximations can be if we don't account for all the forces. Yep, so that was my lecture, and thank you.